All right, so what we're going to do today is we're going to start chapter 19. And what happens in chapter 19 is we've got this idea of charge from the previous chapter, and we've got this idea of the Coulomb force law. And what we're going to do now is we're going to go back to chapter 7 of last semester, where we first learned about energy conservation. And we're going to apply the concepts of energy to this new force that we've been talking about this semester. All right, that's the plan. We're going to think about how does energy work with this new force. So that requires us to remember a couple of things from last semester. So let's see if we remember anything. What's the definition of work? You guys remember what work is? I don't know. We're all on mute.
Is it FB cosine something?
Got it in one, Terry. That's right. So the definition of work from chapter 7 last semester was that work was equal to the force multiplied by the distance times the cosine of the angle. And the angle in question is the angle between the force and the distance.
You said that's the definition of torque?
That's the definition of work.
Work.
Yeah.
Okay.
And work you can think of as a transfer of energy. So the critical thing about this is this cosine theta part right here. That's the angle between F and D. So if I've got a force in one direction and the object is also moving in that same direction, then what's going to happen is F and D have an angle of 0 between them, and the cosine of 0 is 1, right? So if F and D both point the same direction, the work is going to be just the force times the distance times 1. It's like regular multiplication at that point. But if I have a situation where maybe the distance is sideways, but the force is straight up, now I get a different behavior. Now the angle between F and D is 90. The cosine of 90 is 0. And so it doesn't matter how big that force is or how far you move it. If the two things are perpendicular, it doesn't do any work at all. And of course, what if F is one direction, but D is some different direction, and the angle between them is larger than 90 degrees. So anywhere between 90 and 180, this will be true. Well, the cosine of any angle that's greater than 90 is going to be a negative number. And so sometimes I'll multiply two things together and I'll get a negative answer because the cosine of theta is a negative number. And in general, if the force and the distance are at least a little bit in opposite directions, then the work being done will be negative. If the force and the distance are at least mostly in the same direction, you'll get a positive answer. So negative work is F and D are at least a little bit in the same direction. Negative work is F and D are at least a little bit in the opposite direction. Now, why am I bringing this up? Well, I want to think about the work being done by the Coulomb force. So here's my scenario. I know the Coulomb force says that any two charges are going to exert a force on one another, given by that expression, right, where K is the Coulomb constant, Q1 and Q2 are the size of the two charges in coulombs. R is how far apart the two objects are in meters. And because it's in the denominator, it means that the further apart the charges are, the weaker the force will be. So what I want to do is I want to consider the following scenario. I'm going to start off with a positive point charge. And I'm going to hammer this guy down and stick him right there. Then I'm going to have another positive charge super, super, super far away. When I do this in the classroom, I usually make a point of walking out of the room entirely and standing out in the hallway with my little tiny point charge in my hand. But I can't do that because I'm on camera. So we're gonna go super, 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 super far away, way over here, and have a second positive point charge. So we're going to imagine that the distance from this charge to this charge is infinitely big. Fair enough? Now, if that distance were infinitely big, the amount of force that I would feel would be K times this Q times this Q divided by infinity squared. But when you divide by infinity, much less infinity squared, you're going to get basically zero. So what's going to happen is out here, I'm so far away that the amount of force I feel is negligibly small. But what I'm going to do is I'm going to take this charge and I'm going to move it toward the other charge until I end up some tiny little distance away. And what's going to happen is as I move this towards the other charge, the entire time, because they're both positive, the charge that I'm moving is being repelled. There's a force pushing it to the right. But the object is moving some distance towards the left. So the whole time I'm moving this closer, 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 what's going to happen is the work that I'm doing is going to be F times D times the cosine of the angle between F and D. But the whole way, F is going to be to the right and D is always going to be to the left. The angle between them is 180. The cosine of 180 is -1. So what's going to happen is to go from here to here, the Coulomb force is doing negative work to that charged particle. Now, that's easy enough. But if I go to try to actually calculate how much work I'm doing, I run into a problem. And the problem that I'm having is that the amount of force that this charge is feeling keeps changing. At first, when they're basically infinitely far away, the amount of force that I'm feeling is so close to zero, it might as well be zero. And that means that when I first start to move it, I have a basically zero F, which means I'm not doing any work, or at least not very much work originally. But the problem is, the closer I get, the bigger the force gets. So if I think of this move from here to here as being a whole bunch of little tiny baby steps, what's going to happen is I'll have one baby step where hardly any work is being done because F is so tiny. But now the next little baby step, the force is a little bit bigger, which means I'm doing a little bit more negative work. Then the next baby step, the next baby step, and each little baby step that I take over some tiny little distance, F for each step is a little bit bigger. And so what's going to happen is to go from point A to point B, I have to add up a whole bunch of these little tiny baby steps. And each of these baby steps, I'm doing more and more and more and more work. So if I want to know how much work I do to go from here to here, I got to add up all the work for all those little tiny baby steps. So what I'm basically describing here is calculus, right? Calculus is how we deal with the sum of these tiny little incremental changes, right? And so what I'm secretly doing is some calculus, and I'm just going to tell you the answer, and you're going to know it because this is not a calculus-based class. However, if you've taken calculus, you might recognize that what I'm really talking about is I'm doing an integral. Because each of these tiny little things is a tiny little distance dr. So I'm integrating this with respect to r. And so if you know calculus, this next formula should not be a surprise to you. It should look pretty obvious as to where it comes from. But it turns out that the work that I'm doing to go from here to here ends up being k times q1 times q2 divided by whatever final value of r I end up with, not squared. And to go from here to here, the work was negative. So it's the work that I did going from here to here is going to be k times q1 times q2 divided by whatever final distance I have between the two charges. It looks just like the Coulomb force law, except the r is not squared on the bottom. Nifty. Now, last semester when we talked about forces, we learned about conservative forces. Do you recall what a conservative force is?
What is a conservative? Something that has no movement? No.
So conservative forces were forces for which you could make the following statement. The total work done by that force over any closed path, which basically means like a round trip where you start someplace and come back to where you start, the total work by that force will always equal 0. Right? One of the examples of a conservative force was gravity, right? If I have this pen and I lift the pen upward some distance, the work done by gravity is the force on the pen, mg, that's gravity, times the distance, that's the height that I lifted it to, times the cosine of the angle between F and D, but the force of gravity was down and I moved it up, so the angle is 180. So the work that gravity did going from here to here was negative mgh. However, if I take my pen and lower it back down to where it started, well, on the way down, gravity is still the same strength, mg. The distance is the same height that I dropped it or raised it from originally. But now on the way down, the force is downward and the motion is downward. So the angle between F and D is 0. The cosine of 0 is 1. So it did negative mgh going up, but it's going to do positive mgh going back down. The total work going up and coming back was 0. That's a conservative force. Is the Coulomb force going to be a conservative force? Well,
Whoa.
to go from here to here, I added up all the work for these tiny little baby steps, and I got this, negative blah, blah, blah.
Why did you drop the D times the cosine? Because of it's 182.
What did I drop the D out of the what?
From the work definition, you substituted the F from the Coulomb force law, right?
Mm-hmm.
And then what happened to the D and the cosine theta?
Well, the D, like what I had to do, the reason I'm jumping down from here to here is because I'm secretly doing an integral, but I'm not showing you that because this is not a calculus-based class.
Oh, okay.
So if we were doing calculus, what I would be doing is I'd be saying that the work was the integral of k q1 q2 over r squared. That's F. And then the D is I'm always going tiny little distances, and I'm going to call each of those tiny little baby steps dr. So the D in this formula is what we call dr.
Okay.
So that's what happened to it.
Oh, and then you said the R turns to just the R
Right.
because
Well, then when you do the calculus, it turns into this.
Okay.
So I was just omitting this step because I was trying not to show you any calculus. So pay no attention to the man behind the curtain.
Sorry. No, I need the man behind the curtain. I gotta understand all of that.
Well, you don't, because you don't. All you need to know is this is the formula for the work being done. That's all you need.
Okay.
Yeah, this is a non-calculus based class, so I'm secretly doing calculus to get this formula, but you don't need to know how to get the formula. I'm not going to make you ever do that. Plus, we're gonna go past this in a sec anyway.
Okay.
So, but here's the point. If I take all these little f times d's and I add them all up and I get this on the way back, when I go this way, what's different? Well, the force during this baby step right here is the same going back as it was going in.
But it's
The
possible.
distance is the same as it used to be. All that changed was the cosine of theta, right?
Oh.
On the way in, the force was to the right, but I was moving to the left. So on the way in, the angle is always 180. But on the way back, the angle is going to always be 0. And so what's going to happen is each of these little pieces, the work being done is going to be exactly the same, only where it used to be negative, now it's going to be positive. And so it stands to reason that if I add up all the work on the way back, I'm going to get the same numbers I had before, only now they're positive and everything will cancel out. So the work going from here to here and back again is 0. The Coulomb force is a conservative force. Now, here's why we care about that. Because we said that last semester, every conservative force has an associated potential energy, right? We did gravity, and the potential energy for gravity was mgh. Now, why was it mgh? Where did that potential energy equals mgh formula come from? Well, we defined potential energy as being the opposite of whatever the work was. So when I lift something from the ground up, the work done by gravity was negative mgh, and therefore the potential energy up here was positive mgh. For the Coulomb force law, the work going from here to here was this. Therefore, the potential energy formula for the Coulomb force law is this, where I swap that minus sign out. So this is the potential energy. It's the electric potential energy. That's pretty nifty. And what it means is that I can use this potential energy formula in the same way that I used the potential energy for gravity or the potential energy for a spring last semester. I can do energy conservation problems just like we had way back in chapter 7 last semester, but now I can do it with the Coulomb force law. Cool. How are we doing? Uh-oh.
I'm following.
Okay. No, the little picture like froze, and I was afraid that maybe my camera wasn't working. But you can still hear me?
Mm-hmm.
Because my screen is frozen.
Yeah, your screen is frozen.
Like I can still see the camera, but I can't do the camera controls. Okay, we're gonna work around this. This is nuts. I think it's my
Maybe minimize it, bring it back. I don't know.
I can't even do that. Yeah. I can't swap tabs. Okay, well, let's work forward. I don't know what's going to happen at the end of the meeting because I can't close the meeting out. Let's figure this out. Oh, this is scary. All right.
Did you laminate those yourself? Oh, now he's frozen.
Yeah, he's frozen now.
Like, what we supposed to do?
He's most likely just gonna restart the stream over.
Oh,
He's most likely just gonna start it over.
yeah. Anything?
All right, we're back, and hopefully we haven't lost the thread too much. So we had just learned about the electric potential energy. And because I'm concerned that the computer may have...
I'm still here, Dr. Fleming. We was concerned. What happened?
My computer decided it needed to restart immediately, and it just crashed out. I rebooted, and we're back.
Okay.
So anyhow, we've gotten the electric potential energy. So this is the potential energy for the Coulomb force law. And what's cool is that we could use the Coulomb potential energy to solve the same kinds of problems that we used to do back in chapter 7 last semester. If you're under the influence of conservative forces and nothing else, that says your energy is conserved. So for instance, my starting kinetic energy plus my starting potential energy has to equal my final kinetic energy plus my final potential energy, right? We used this a whole bunch last semester, but there we were always dealing with either gravity or sometimes springs for your use. Now we got a new kind of potential energy, but other than that, it's exactly the same. So let's imagine a scenario where I could put this into play. Imagine I've got two charged particles. So this guy over here is 50 microcoulombs, and this guy over here is, heck, also 50 microcoulombs. And I'm going to place these guys 10 centimeters apart. Now, I'm going to nail this guy in place. He can't move at all. But this guy is not nailed in place. I'm going to release him from rest. And what's going to happen is because he's repelled from this guy, it's going to end up traveling under the influence of the Coulomb force until later it arrives some distance away. Let's say that this is something like 2 meters. And if this particle has a mass of, how about 10 grams, what I would like to know is, by the time it gets here, how fast is it going? Well, at this point, I have all the information that I'm ever going to need to solve this problem. Because what's going to happen is my particle started here, it finished out here, it started at rest, so it had no kinetic energy, but it was very, very close to the other charge, which means it had a large amount of potential energy. As it moves further away, this is getting smaller. The potential energy at the end is smaller than it used to be, but to make up for it, the kinetic energy is getting larger by the same amount. So I can use this expression to solve for the final velocity. So let's put that into practice. I need to remember what the definition of kinetic energy is. You guys remember what K is?
No, I don't.
So kinetic energy was the energy invested in the velocity of an object. And the formula for it was 1/2 m v squared, right? This is why I gave you the mass of the things, because I knew I was going to need it when I did this. Now, if the particle is here at rest, it's got a velocity of 0 at that moment. That means that if that velocity is 0, my starting kinetic energy is conveniently also 0. However, when it's here, it's got some potential energy. It's given by this expression. So I'm going to have U initial is K times Q1 times Q2 divided by R. But which R? Well, it's the R when he's here, which is from here to here, 10 centimeters. So I'll call that R1, but I know that R1 is going to equal 0.1 meters. Remember, I had to convert from centimeters into meters. That's why it's 0.1 and not 10. Nifty. So that's my U initial. Now that has to equal K final, but K final is going to be whatever 1/2 mv squared is when he gets over here. And we'll be solving for V. Meanwhile, plus U final is the potential energy when I'm all the way out here. So plus K Q1 Q2 over, I'll call it R2, but R2 is the whole 2 meters. So now all I've got to do is crunch the numbers and solve for V. So I'm going to move this to the other side. So I'm going to have K Q1 Q2 times 1 over 0.1 minus 1 over 2. All I did was I took the K Q1 Q2 that both of these terms had in common and I factored it out. That's going to equal 1/2 mv squared, because this is still over on the other side. Then I'll get rid of the 1/2 by multiplying by 2. I'll get rid of the m by dividing by m, and I'll square root everything. So I'm going to have 2k q1 q2 over m times 1 over 0.1 minus 1 over 1/2. You have a question? If you don't, I'm going to mute you because your bird's chirping. Yeah.
No, I did have a question. That's what I was about to ask. But so you said to get the 2/2kq over the m.
Yeah, I wanted to get rid. I wanted this 1/2 to get out of here, so I multiplied both sides by 2. That's why this canceled, and it became that 2 over there.
Okay.
I wanted this m out of here, so I divided both sides by m, which is why the m's on the bottom over there.
Okay.
And then I wanted the square to go away, so I square rooted both sides. That's why it's a square root. That's all it was. So now I can just plug in all my numbers. So 2k is still 8.99 times 10 to the 9th. The Q1 and the Q2 are both the same number, right? It's 50 microcoulombs, so 50 times 10 to the negative 6. Instead of writing that twice, I'm just going to square that bad boy. The mass is 10 grams, but I need that to be in kilograms because that's the SI unit. So 10 divided by 1,000 is 0.01. And of course, I have 1 over 0.1 minus 1 over 1/2, or 1 over 2. 1 over 0.1 is 10. 10 minus 1/2 is 9.5. So this entire thing right here is going to be 9.5. So now all I've got to do is crunch some numbers. And so I get a whopping 206.6 meters per second. By the time this thing has gone from here to here, and I mean, that's like it went 190 centimeters. That's basically not even 6 feet. By the time that thing has moved not even 6 feet, it's already traveling 2/3 of the speed of sound. That's insane. But it's because the Coulomb repulsion is so incredibly strong. So, bottom line is you can do energy conservation problems just like you used to back in the day. So far, so good? Let's make it more complicated. Now, what we're going to do next is something that hopefully will make sense by analogy. So, if you recall, we started this whole discussion of charges and the Coulomb force by doing the Coulomb force law. And the Coulomb force law looked like that. But then immediately we said, man, it really sucks to have to keep talking about charge 1 and charge 2. And so we invented the concept of the electric field. We said the electric field was going to be defined as how much force you feel divided by the size of the charge that was feeling it. So this was the definition of E. And what's going to happen is, since this F is K Q1 Q2 over R squared, and I'm dividing by one of those Q's, whichever Q I'm dividing by ends up canceling out. And so we instead got this concept of the electric field. And the cool thing about the electric field is that we're talking about what one little charge is doing. We're imagining that if you have a little piece of charge, it creates a disturbance, this invisible distortion all around itself. And if there's other charges around, they will interact with that distortion and it will cause a force, right? This force. However, even if there's no other charges around to feel the force from that disturbance, the disturbance is still there, right? The analogy we used the other day was putting a bowling ball on a waterbed, right? If there's other things on the waterbed, the weird dip in the shape of the bed is going to push those objects around and cause forces. But even if there's nothing else on the bed, if you put a bowling ball on it, the shape of the bed's going to get all messed up. And so the electric field is like the weird curviness on that waterbed when you put a bowling ball on it. That's the way we're thinking about it. And by measuring the electric field, we're talking about the weird shape of the distortion, and we don't necessarily have to specify any other particles. One charge creates a disturbance, whether anyone's around to feel it or not. Now, here's why that's cool. Well, this chapter, we've started with the concept of the electric potential energy. And you'll notice there's a whole lot of similarity between some of these formulas, right? Here we had K Q1 Q2 over R squared. Here we had K Q over R squared. Over here I have this, which looks almost exactly like the Coulomb force law, except the R isn't squared. But we still have that annoying problem of, in order to talk about the electric potential energy, I've got to talk about both charge 1 and charge 2. That's irritating. So I'd like to have something that's sort of like the electric field, except in terms of energy, not in terms of force. So whereas the electric field tells me how many newtons I have to have per Coulomb of charge that's feeling a force, Over here, I want to talk about how much energy it takes to put a charge in a certain location per coulomb of charge that I put at that location. And so we're going to invent a new concept that's kind of similar to this. And we're going to define that concept to be whatever U is at or for two charges divided by the size of one of those charges. We're going to give this a name. We're going to call it V. And this is where I'm going to run into problems, is because I didn't make up these stupid names, right? Somebody else did. And some of these names that we've chosen for these concepts are unfortunate because it can lead to unnecessary confusion in the hands of many of my students. So it's critically important that you get the nomenclature correct. When I'm talking about U, this is the electric potential energy. Right? The electric potential energy is measured in joules, just like any other potential energy. But this thing here, this concept V that we've just made up, it has a name. It is called the electric potential. Full stop. It's the electric potential. That's really annoying because they're related concepts. They have very similar names. Students get them confused. So if I say electric potential energy, I'm talking about U. If I say electric potential, I'm talking about V. Now, U is measured in joules. What are the units for V? Well, if this is joules, that's joules divided by charge, which is coulombs. So joules per coulomb. We're going to give that a name. A joule per coulomb is a volt. That's what a volt is. It's a joule per coulomb. And notice if U looks like this, but then I'm dividing by one of those two Q's, that means that whatever Q I'm dividing by cancels out. And so my formula for the electric potential of a point charge looks just like my formula for the electric field, except the R is not squared. So I can already tell you, because it happens every semester, maybe it won't this semester because the sample size is so small. There's, I believe, 6 of you enrolled. The last of you just validated yesterday, so you're officially, there's 6 of you. But every semester, there is at least one student who gets a problem on an exam. And in that problem, I ask them to calculate one of these 4 things. And somebody, every semester, when asked to solve for one of these 4 things, they end up solving for one of the other 4 things, right? I'll ask them to find the force felt by a charge, and all of their problems will have kq over r squared. Or I'll ask them to find the electric potential energy, and they'll have kq over r instead of this. And when that happens, my response is to put a giant red X on that problem and not give them any points, right? It happens every semester to somebody. So please make sure that that somebody is not you by knowing the difference. This is the force. This is the electric field. This is the electric potential energy. This is the electric potential. This is for point charges. This is for point charges. These are the definitions of E and V, respectively. Make sure you get them straight, because I will be merciless about partial credit for people who screw that stuff up. So, I guess that's kind of nifty. There is, however, a really huge difference between the stuff on the left-hand side of this page and the stuff on the right-hand side of this page. Because when we deal with forces, or when we deal with electric fields, both of those things are vectors. So if I gave you a bunch of point charges and I asked you to find the total force felt by a charge, right? You've got homeworks where you did that in chapter 18. And in all of them, you had to find the magnitude of E or F or whichever you're doing. That's the number part you get from the formula. But then you had to break those formulas down into X and Y components, then maybe add all those vectors together, and then maybe recombine those vectors at the end. You had to deal with lots of vector stuff with all this stuff. That's kind of a pain in the butt. Good news for chapter 19. Potential energy, it's just a number. There's no direction associated with it, which means I don't have to break it into components. The electric potential, not a vector, doesn't have a direction associated with it. It's just a number. Now, it is not a vector field, but a scalar field. So if you have a particle, the electric potential will have different values at different locations depending on where you look. And that's what R represents, is how far it is from the charge who's creating the electric potential to the location where I'm measuring the electric field. But the cool part is, all you got to do is add them up. It's super easy. Let's do that. So here's a collection of point charges. Let's have 100 microcoulombs. Let's have this guy be 50 microcoulombs. And let's have this guy over here be negative 20 microcoulombs. And let's put these on a rectangle. Let's have this be 10 centimeters. Let's have that be 15 centimeters. So I've got three charges: charge 1, charge 2, charge 3. And let's figure out some of these new concepts here. Let's do the electric potential energy first. All right, I want to find the electric potential energy of those three charges. So what's the formula for the electric potential energy? Well, the electric potential energy is K Q1 Q2 over R. So all I got to do is utilize this. Except, wait a second, I've got three charges. My formula only has two Q's in it. So how do I respond? What do I do if I want to find the electric potential energy, not just of two charges? If I just gave you this would be super easy, right? If I gave you this would be super easy. All three, not so much. What do I do? We throw up our hands in frustration. So the way to think about this problem is to think conceptually about what this formula represents. When we went through that whole process, right, we got that formula by imagining that I had two charges that started super, super far away. But what I did was I moved one of them closer until they were some distance away. And what the potential energy represented was how much work the Coulomb repulsion was doing the entire time I was putting them close together. That's how to think about it is that the electric potential energy represents how much work it takes to put those charges that close together. So if I think about it that way, the potential energy of all three of them is going to be how much energy I had to expend in order to put all three of those charges that close together. So to find the electric potential energy, what I'm going to do is I'm going to imagine assembling this set of charges from scratch. And I'm going to keep track of how much work the Coulomb repulsion did while I was assembling them. Now, if I imagine having a blank slate, none of these are present at first, and then I go off to infinity and I'm going to grab one of those charges, and then I'm going to take that charge and put it at its current location. So if I do that with none of these here, and I go out and I grab that 100 from way off, super far away, and I stick and put it here, the amount of work done by the electric field during that process was 0. Why 0? Because I only got one charge right now. And if I've only got one charge, that one charge didn't have to fight against any of the other charges. So the first one I got for free. I didn't have to do any work to bring the first one out because there's nobody out here to push him around. But then I'm going to go back out to infinity. I'm going to grab the second charge, this 50 microcoulomb charge. And the entire time that I'm bringing that 50 microcoulomb charge in, it's being pushed on by the 100 that I've already placed there. It takes a certain amount of work for me to put this guy that close to him because they're repelling the entire way. And so the amount of work that that would take just to put him and him next to each other would be K times Q1 times Q2 divided by how far apart they are at the end, but they're going to finish with an R of 0.1 centimeters, or 0.1 meters, or 10 centimeters. That was easy. But that's just getting those two next to each other. I got to add this one here as well. So I'm going to go back out to infinity. I'm going to grab this negative 20 microcoulomb charge. And what's going to happen is as I bring this guy in, it's going to have to fight against both of the charges that are already there. And to know how much work it would take just to fight this guy, I can ignore this one. And to fight against this guy, it would be plus K Q1 Q3 divided by R. But for that one, R would be this distance, which is 15 centimeters or 0.15 meters. But I'd also have to fight this guy against this guy. So I'd add in K Q3 Q2 divided by, what's R? Well, R would be the distance from here to here, which is that little diagonal line. And of course, I can get that from the Pythagorean theorem. So 0.1 squared plus 0.15 squared. And so the potential energy of all three of them I would get from something like that. Nifty. What if I added a fourth charge? Right? I'm going to go in. I'm going to add another charge. Let's let this one be positive 100 microcoulombs again. And I'm going to put him in the fourth corner of this little rectangle. Well, how's that change my answer? Well, the amount of work it took to assemble these first three guys, we've already calculated. And all I'm going to have to do is a little bit of extra work to add in this guy. Now, this guy, when I bring him in, is going to have to fight each of the previous three. So when I add in the fourth term, or the fourth charge, I'm going to end up getting not just one term, but one for him and him, one for him and him, and one for him and him. I'm going to get 3 more terms. So I'd have to add plus K, this is number 4, Q1, Q4 divided by Well, 1 and 4 is this distance apart. Plus, now I'm going to have K, Q2, Q4. And 2 and 4 are 15 centimeters apart, so 0.15. Plus, then I'd have these two, K, Q3, Q4, over 0.1. So that was super easy. Now, something else I should point out, because it's not obvious. Back when we were doing the Coulomb force and the electric field, both of these were vectors. And what that meant was that we only used the formula to find the magnitude of the force or the magnitude of the electric field. By definition, magnitudes are always positive. So even if one of my charges was a negative number, I would never plug a minus sign into this formula. I'd always plug in positives here. And the reason for that is because even if I had a positive charge, but I'm finding the electric field, say, over here, well, even though this charge is positive, at this location, its electric field pointed in the negative direction. So I might still want to have a minus sign on this electric field when I break down the components. If I had a negative charge, and I was looking at the field on the right-hand side, even though this is a negative charge, the field points towards it. So this electric field would be in the positive direction. So the pluses and minuses all came from what direction the arrows were pointing, not what sign the charge had. But for these two things, they're not vectors. They don't have a direction, which means if I'm dealing with the electric potential energy or the electric potential, and I have a negative charge, I'm going to put a negative number in for Q. I won't put in the absolute value. I'll put in the actual negative value. Now, the reason that matters for us here is because if I were to go evaluate these expressions, and I'm not gonna because I don't really care what the number is, but if I was gonna, then what would happen is when I get to Q1, Q1 would be a positive number. Q2 would be a positive number. So I'd have all positive numbers for this term. So this would for sure be a positive number. However, when I go over here and do Q1, Q3, Q1 is positive, Q3 is negative, this is going to give me a negative number. So I'm going to have some terms that are positive, other terms that are negative. Q2, Q3 is going to have a negative Q3 and a positive Q2. That's going to be a negative number. Over here, Q1 and Q4, they're both positive, so that's positive. Q2 and 4, negative. Q3 and 4, negative. Oh, sorry. Q2 and 4 is positive because this is a positive one there. So what's going to happen is several of these terms are going to be negative numbers. It is entirely possible to have a negative amount of potential energy. Now you might wonder, well, what does that even mean? How would I have a negative amount of energy? That seems crazy. But one way to think about it is that if I have two particles and I bring them together and their potential energy is positive, that means that the Coulomb force was doing negative work while I was bringing them together. It was storing up energy. So as I have two positives and I bring them close together, the Coulomb force is fighting me the entire way. It's doing negative work and it's taking energy away from me as I push, and it's storing that energy up. So that now these two positive charges are super close together, but they've got all this energy sort of stored up inside them. And if I let them go and they fly apart again, I'm going to get all the energy back. Compare that to a positive charge and a negative charge. Well, if I'm bringing a positive charge and a negative charge together, I don't have to fight them because they want to come together on their own. In fact, I have to actually pull to hold them apart. If I let go, they're going to go stick together. So if you have a negative potential energy, the fact that it's negative represents that the fact that I had to do personal myself work to pull them apart and keep them apart, as opposed to when there was positive potential energy where I had to do work to squish them together. And that's the whole idea. So do bear in mind, you can get values that are positive or negative and keep track of your signs accordingly. Now, this was me asking for the electric potential energy for these point charges. What if I was asking for something different? Let's take Q4 back out, remove him. And this time what I want to do is I want to find the electric potential at some location. Let's find the electric potential at that one spot due to the first three charges. So 100, 50, so I want to find the electric potential at that location. There's no charges there, but the electric potential tells me how much energy it would take per Coulomb to put a charge there. That's what it's telling me. So I'm finding the electric potential, which for a point charge is KQ over R. But I've got three charges, so I'm just going to do it 3 times. So my total V is going to be V1 plus V2 plus V3. So KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3. And all I got to do is plug in and fill in the blanks. So for KQ1, 0.99 times 10 to the 9th times 100 times 10 to the negative 6 divided by this distance, but that's that, which we've already figured out, plus for the KQ2, it's going to be 8.99 times 10 to the 9th times 50 times 10 to the minus 6 divided by, well, for this guy, from here to here is 15 centimeters, plus, ran out of room, this 8.99 times 10 to the 9th times Q3, which is negative 20. And that's it. And again, I could crunch these numbers and get a value. But knowing how to do it is really all I care about. How are you doing? So far, so good?
Yes.
Good reason.
It's easier in another direction isn't involved.
Yeah. And in fact, what you would find is that if you were to go on and take like a higher level version of this class, right, and learn some of the more complicated concepts, what often happens is we don't talk about like the electric field nearly as much in more advanced classes because, man, it's vectors and they're super hard to deal with. And a lot of times with really complicated problems, what people will do is they'll solve for V first because V is easy. There's no vectors, there's no direction. But then once you know V, it turns out that V and E share a connection. So a lot of times you can get V super easily and then use that answer to calculate E way, way easier than it would be to calculate E directly. And that's where we're going next. I want to think about how the electric potential and the electric field are related to each other because they are related to each other. Now, to see how, let's swap to another screen share. But this time, what I want to look at is another one of my favorite little physics simulations. So this little physics relation will take small point charges, and it will allow me to look at the electric field or the electric potential at different spots. So here's a 1 nanocoulomb point charge. Now, all the arrows that you see here, these are just denoting the direction of the electric field at that spot. And the brightness of the arrow tells me the magnitude of E. This is perhaps sort of annoying because they can only draw arrows in certain locations. What I'm going to do here is I'm going to pull a little sensor out. And if I put a sensor right here, you can see that now it's drawing this arrow to scale. So when E is large, the arrow is long. And as I move further and further away, the arrow is getting shorter. So I can put sensors in different locations, and you can see that the direction of the sensor always matches up with the stupid arrow wherever I'm at. But now I can move them around a bit more freely and measure in any places that I want. So this sensor shows me what my electric field is doing in any location. Now, it can also show me the electric potential. Because electric potential is measured in volts, sometimes I'll refer to it as the voltage, because it's way easier to say voltage than it is to say electric potential. So the sim will do that with color. You can see that like when it's super, super bright red, the electric potential is really, really large and positive. But as it gets lighter and lighter and lighter, that's the electric potential getting smaller. Now, that's not super easy to determine because it's hard to tell how different this bright red is from this bright red. So I'm going to turn both of these off and instead use a sensor. And so what's going to happen is anywhere I put this little target, it's measuring the potential at that spot. So like right now, at this location here, where I am this distance away from the positive charge, my electric potential is 8.265 volts. If I move it closer, you can see that the electric potential is getting bigger. Well, duh, I'm making R smaller, so the smaller R is, the bigger V ought to get. If I move further away, V is getting smaller. So far, so good? Now, one thing that's interesting is, like if I put my little target right here, and it's like 12.44 volts, if I keep my thing, if I go up the same distance, I can't quite get it. At this location here, the potential is the same as it was where I was a minute ago. So there are lots of different locations where the potential is the same. If I hit this little button, that little green line is what we call an equipotential surface. And what's happening is everywhere on that green line, the value of V is the same. And you'll notice it's a circle. Why is it a circle? Because everywhere on that circle, the R is the same number. So you can see that right there, it's 11.81 volts. If I go over here, 11.81 volts. Over here, 11.81 volts. So everywhere on that surface, I have the same value of V. If I go further away, I get another equipotential surface, but here it's 6.998 volts. If I go even further, I can make more equipotential. So anywhere I go, I can draw equipotential surfaces. And for a single point charge, my equipotential surfaces, they look like concentric circles. This is not super surprising. Now, I want to imagine having a little positive charge. Imagine that I put a little positive charge right here at this equipotential surface where the potential is, what do we say it was? 11.81. Well, that's this one. Nope. Or 12.11. So what's going to happen is if I put a little positive charge at that spot, it's going to take a certain amount of energy to get that positive charge this close to this other charge. If, however, I put that positive charge somewhere else on that surface, the amount of work it takes to put it here is the same as the amount of work it takes to put it here or here. Anywhere on that circle, it takes the exact same amount of energy for me to push that particle to that location. That implies that if I want to go from point A to point B, if I move from one point on the surface to a different point on that surface, it shouldn't take me any work at all. It's basically free. I don't have to expend any energy to move around on an equipotential surface. The other way to think about this is to think about the forces felt by a particle on that surface. And one thing that I will want you to pay attention to is look at that sensor. Look at the direction of that electric field and compare that to the equipotential surface. And as I move this around the equipotential surface, what can you tell me about the orientation of my electric field and my equipotential line? I'll put some more sensors out at different locations. And what I'm looking for is to see if you can find me a pattern. What's the relationship between these equipotential surfaces and the electric field? Do you see it? No, Dr. Fleming, we all went to sleep. Your class is boring. So the thing that I'm hoping that you would see is that my electric field, no matter where I go, always points radially away from the charge. It's always pointing away from the positive charge, no matter what. And that means that my equipotential surface is always tangent, or sorry, the electric field is always tangent to that extra, or it's perpendicular to the tangent line at that location. In other words, if you look at this spot right here, at the place where I had that sensor, the tangent line to the equipotential surface looks like this. E is perpendicular. This right here is a right angle. If I look over here, there's my tangent line, perpendicular. If I look over here, there's my tangent line, perpendicular. Everywhere on the equipotential surface, my electric field is always perpendicular to the tangent of that equipotential surface. Now, to see why that is, remember that the electric field always points the same direction as my force. But on the equipotential surfaces, if you move around the equipotential surface, you're never doing any work. Well, why are you not doing work? Because the force is one direction, but if you're moving along the surface, you're moving perpendicular to it. That's the FD cosine theta, and the theta in this case is 90. So in general, what you will find is that equipotential surfaces will always be perpendicular to the electric field at any given moment. And that's interesting, not so much when I have something boring like one positive point charge. What if I have more than one charge? So now my electric field lines are super complicated, right? They're starting on the positive, but ending on the negative. That's nasty and ugly. But that also means that my electric fields and electric potentials are more complicated, right? Now, my electric field doesn't necessarily point to or away from any one charge. It can point all kinds of different directions depending on where I look. Because what I'm doing is I'm adding up the E from this, the E from this, and the E from this, and getting the final answer. This is the total of all the E's in that location. It also means that my equipotential surfaces are more complicated. Sometimes they're going to look roughly circular like this. Other times, they're going to be weird. And what's going to happen is if I just kind of map out a bunch of equipotentials, you can see that I've got a very unusual looking pattern, right? Everywhere on each of those surfaces, V has a single value. But look what happens when I put my sensors out here, right? At that location, as complicated as all this is, here's my tangent line, and at that point, that's a right angle. If I put the sensor someplace else, well, at that location, here's my tangent line, still 90. If I put my sensor, say, right there, there's my tangent line, still 90. No matter where I go, they're always perpendicular. That's pretty neat. And it also will help us figure out some stuff in places that are more complicated. Hang on, bear with me for a second as I wrestle with the controls for this stupid thing. So what if I had that same parallel plate capacitor we were talking about yesterday? Just to remind you, I have a metal plate that I'm looking at the edge of, another metal plate that I'm looking at the edge of, and a little gap in between. And I'm going to put a bunch of positive charge on one of the plates and an equal amount of negative charge on the second plate, right? We drew the electric field lines for this the other day. Let's swap colors. So the electric field lines went from positive to negative. So in the gap, they looked like this. And outside the gap, They were much more complicated, right? If I wanted to sketch the equipotential surfaces, well, the equipotential surfaces would always have to be perpendicular to E at any given location. So notice, since E always points straight down everywhere in the middle, my equipotential surfaces in blue would be this. But then what's going to happen is like straight down the middle, I'm probably going to have one. But as I get closer to the bottom, they'd have to bend outward so that at this point, they make a right angle. At this point, they make a right angle. And that's going to cause it to bend one way or the other. And in fact, if you continue this pattern on, what will eventually happen is they always form closed loops. So I'd have something like this, and this would loop around something like this. This would go straight down the middle. But your equipotential surfaces would look something like that. Does that make sense? So this is pretty cool. And the reason it's pretty cool is because right here in the middle where the electric field is nice and happy and uniform, we're going to be able to find a really easy way of connecting the electric potential to the electric, the Coulomb force. It's going to be more complicated in places out here where E is messy and ugly. But right here, it's super, super easy. And to make sense of it, I want to consider, let's do it on this page actually. Let's consider if I had a little positive charge and I put that positive charge here and I moved it from here to here, from one side of the capacitor to the other. Now, what's going to happen is I know that the definition of V is U over Q. Right? That was the definition of the electric potential. But one of the things that's kind of annoying about the sorry, somebody like delivering something at my front door, I think. The electric potential energy, or any kind of potential energy, is unique in that where we put zero is kind of arbitrary. If you recall, last semester when we talked about the about the gravitational potential energy, MGH, we could always pick any place we wanted to be height zero. And it didn't affect our answers at the end of the day. And the same thing is true for the Coulomb potential energy. Where zero is entirely up to us. Now, for point charges, we've kind of already made that assumption tacitly. For a point charge, we always use this formula here. But where is that formula going to be zero? At infinity, when r is infinitely far away. But we could always have picked someplace else if we wanted to. The reason that's important is because since the 0 point of U is arbitrary, the 0 point for V is also always arbitrary. I could always just pick a spot and say, by God, this little line right here, this is V equals 0. Now, if I call this V equals 0, then the V at this location would be some different number. Maybe it's 10. But what if somebody else said, no, 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 I don't want this to be voltage 0. I want this to be voltage 0. You could make that choice too. However, if this was voltage 0, what will always be true is that this will be the same number of volts different from here to here as it was in the other case. In other words, I have two possibilities. I could call this V equals 0 and this V equals 10, and that's perfectly valid. Or I could choose to call this V equals 0. But if I do that, this was 10 volts lower than this. So this has still got to be 10 volts lower here. So if this is V0, this would be V equals negative 10. Either way, what's going to matter is that the potential at this line is going to be a certain number of volts, 10, more than this one. They're always going to be related by that same constant. So what we care about with electric potential energy, and therefore with electric potential, is often not the absolute number for U or the absolute number for V, because we can always shift that up or down by any constant if we wanted to, but rather the difference from point A to point B. So from here to here, the change in potential energy is a certain number of joules. The change in potential is 10 volts, always. If this is V equals 1,000,000, this would be V equals 1,000,010. So when we talk about this, there's a term we often use for delta V called the potential difference. And it just means how different V is at one location compared to some other location. And regardless of where we call 0 volts, the potential difference will always be the same no matter what. Here's why that's helpful here. I'm going to move this little charge from one plate to the other plate. That means that V has one value where it started. It's going to have a different value at the other side. The potential difference from here to here is going to be some number. And the potential difference will be the change in potential energy over Q. So let's think that through. Delta V is going to equal delta U over Q. Except wait a second. The potential energy in general was the opposite of the work done. So that means that delta U is just going to be the amount of work done either way. So what I care about is how much work got done going from here to here. If I want to know what delta U is, it should be the work done going from here to there. Cool. What's the definition of work? Force times distance times cosine of theta. Okay. So I'm going from here to here, and I'm thinking about how much force I feel. Well, but wait a second. The force is related to the electric field. And the electric field inside this gap we said was constant, right? That means the amount of force that I feel is also constant. And the amount of force that this guy feels going from here to here is going to be however much charge this guy has, Q, times however big that electric field is, E. Cool. So the work will be Q times E times D, where D is the distance that it moves. Well, D is just going to be the size of the gap between those two plates. Cool. So now I've got Q times E times D. That's delta U is the work, right? With a minus sign divided by Q. Oh, notice Q over Q cancels. It doesn't matter how much charge I put here, because the bigger charge I put there, the more force I'm going to feel, the more work it's going to be. And since V is per charge, the effect exactly cancels. So look what I've got right now. I've got a relationship between the difference in V from here to here and E times D. Now that minus sign is important. It means that if I go from here to here, and I'm going in the same direction as the electric field, delta V is negative. In other words, the electric potential always gets smaller if you go in the same direction as the electric field. Cool. And in fact, the way we sum all this up is we usually rearrange this and we say that E is negative delta V over D. What does that even mean? Well, the way I like to think about it is it says that the electric field is related to how much V changes when you go from one place to another. If you take how much V changes divided by how far you moved, that tells you how big E is. If you have a place where there's no electric field and you move from point A to point B and there's no electric field, well, the electric potential at point A and point B have to be the same. If E is 0, that means delta V is 0. So if I go from point A to point B and there's no electric field in between, then that means that V here might be 1,000, but V here would also be 1,000. Delta V going from point A to point B would be 0. If, however, here V was 1,000 and here V was 10,000, so going from point A to point B caused V to go way up. That means delta V is positive. The electric field, therefore, would be the opposite direction. So if V is small here and big there, and I go from point A to point B, the electric field is going to point in the opposite direction. E points in the direction that V decreases. That's what that minus sign means. So we've got a relationship between the electric field and the electric potential. And a lot of times it's easier to figure this out and then use this to calculate that. Now, one little bit of caution. I will point out two things. One, we made the assumption in here that the electric field was uniform, that the field was the same the entire way. And the reason that mattered is because if the field was the same the entire way, the force was constant. It wasn't changing. If I'm out here where E is changing directions constantly, it's a way more complicated problem to solve because then I've got to do some calculus. And in fact, this formula only works for uniform fields. If the field is not uniform, then it only works if D, the distance that I move, is vanishingly tiny, right? Basically, it turns into a derivative. So this is only true for uniform fields. It will not work for fields that are not constant. Although, as we're going to see in lab later, it turns out that sometimes you can get away with using this and get a pretty good answer, even if the fields aren't uniform. But we're going to save that problem for a laboratory down the line. All right, so we've got this concept of electric potential and electric potential energy. We've seen how it's related to E. What we'll do next time is we will play a little bit more with the concept of these capacitor plates, and we'll learn how to do this for some stuff that's a lot more practical and a lot less weird and theoretical. So hopefully you guys stuck with me on that one. I'm calling it a day. I will see you guys later. Any questions? All right. Have a good one, Terry.